All right, this should be the third lesson you're looking at, or the third part of your notes you're looking at, and I wrote in all the answers that we got from previous videos. Hopefully, you've also done a little practice on some of those practice sheets, and I have some other things that I'm going to send for you to maybe help you out a little bit. But I wanted to talk about some of these that are left. So I wanted to talk about this one down at the bottom in the middle, because it is a power rule. It just doesn't look like it. There's no quotient rule. There's no power rule. There's no product rule. In antiderivatives, there really is only the power rule. That's it. Everything else you have to remember backwards, or use some algebraic strategies to make it in to some of those big lists of antiderivatives that I put out there for you on the last video. So this one requires a little bit of algebraic manipulation, and it's one that we can do to easily make it just into a simple power rule problem. I found a little bit thinner pen, so I'm hoping that'll work a little better today. So I'm going to use the distributive property to look at this as two separate fractions. Oops. I hope you didn't see what I just put up there, but it was trying to do a little extra stuff with the video. Thus my oops. Just a little screen popped up. All right, so if I split this into two fractions, basically by saying that it's this divided and that is a fraction. If you think about it, it's like saying 2/4 plus 1/4 equals 3/4. It's just you're going backwards from that. You're splitting up the 3/4 into 2/4 plus 1/4. We're just doing that way. So we took the common denominator and split it back apart into two fractions. Okay, so now we can simplify that into x to the 1/2. I need my integral sign. I didn't write that because x to the first divided by x to the 1/2 is just x to the 1/2 subtract exponents. Plus, now I'm going to change this second part right here. The second part, I'm going to change that into a power. And that as a power is really written as x to the negative 1/2 because it's a square root, but it's in the denominator. Don't forget your dx, your differential. That's really important. Sometimes in the AP test, they have decided to choose not to see it if you don't write it, but there have been years I hear that they have simply counted it wrong. So try to remember it. It's definitely important. It'll be hard to see the importance of it until you look at applications so much, but you really need it. All right, so now I'm going to use the rule that if I have an f plus a g, two functions added, I can just take the antiderivative of each part, and I can use the power rule for both of those since they're powers. So I'm going to add to the exponent, add 1. 1/2 plus 1 is 3/2, 1.5. And I honestly, you can write the 3/2 here, but I'm a lazy bum, and I have gotten to the point where I can just say, okay, I'm multiplying by the reciprocal. So instead of dividing by 3/2, I'm going to multiply by 2/3, and I never write that. I just simply go straight for the reciprocal because I tend to make mistakes, and I hate having extra steps. So I tend to do that right away. That's a personal preference. Then if I have added to x, now I have to add 1. Negative 1/2 plus 1 is 1/2. Now divide by 1/2. That is the same thing as multiplying by 2/1. So I'm going to write multiply by 2/1. Don't forget your constant of integration because, all right, sorry, I had a little pause there. Because if you don't have the constant of integration, you're missing out that there's actually a whole family of antiderivatives for every single function. It could be that. So this, I'm going to just say that's big F. Remember, big F is how you label antiderivatives, or big G or big H or whatever. But if you want to check if you are correct, you can always take the derivative. And I often do that just to double check. So taking the derivative, remember you have to go backwards. So I'm going to bring the coefficient down. Okay, that's that 2/3. And then I'm going to subtract 1. Well, that's 1/2. But you have to multiply by that exponent. And do you see how they cancel themselves out? Plus, and so we got back to this. Yay, that's what we needed. Plus, if I leave the 2, bring the 1/2 down, but subtract 1 off of my exponent, and then if I take the derivative of this plain old number, that's a plus 0. So look at this. My 2 and my 1/2 cancel. I'm back to that negative 1/2. That's exactly what I had here. So I get back what I started with under the antiderivative sign. That's what I love about antiderivatives. If you just take the derivative, which I find easier because I'm so much better at them because I do them so much more, I think, then I can easily just see my answer is right. So I took the derivative. I got my back what was under the integral, in the integral sign. I say under the integral sign. I think most people do as well. But I get back what I started with under the integral sign. So I clearly got it right because I have a function that if I take the derivative, I get back what I started with. Okay, so let's do some of these trig ones. So I want to come back with my little pen here. All right, thank you. Get setting up. So if I want to take the antiderivative of sine, we're going to do this sine x one up here. Oh, my computer's trying to mess with me here. All right, so if I want to do this guy up here, remember there's a little rule that says if there's this number in front with derivatives, you can just bring it out in front. You can just forget that it's even there. So you can write it like this. Oh, man, you can if you can read my handwriting. I'm going to try that one more time. I'm just going to write it below. There's a little box that's getting in my way on here. So, okay, so let's try this way. You can write it like this. Much better. Okay, you can write it like that. And then you can take the antiderivative with the 2 just kind of on front, just like with derivatives. You can just bring along for the ride. As long as they're not a variable, you cannot take a 2x out front, for instance. Variables have to stay in there. You have to take their antiderivatives just like you have to take a derivative. There's a special rule. If there's a product, there's not a product rule, but you can actually do some algebra manipulations to make it look like a power rule sometimes. Okay. Or you can do this cool thing called integration by parts, which is not part of the AB course. It's part of the BC course, and it's not part of any course this year. So, all right. So we're going to take the antiderivative of sine. So if I have to take the antiderivative of sine, that means I have to kind of think backwards. What gives me a derivative of sine? Well, cosine does, but cosine gives me a derivative of negative sine, so it's negative cosine. So my antiderivative of sine is negative cosine. Okay, it's kind of backwards. Now I had the biggest problem remembering which one was negative. And so I just always took the derivative. So if I, plus C, don't forget your constant. I told you I'd forget it sometimes. All right, so I'm going to rewrite that as negative 2 cosine x plus C. That's my antiderivative. And if I want to check it, just take my derivative. If I take the derivative of this whole thing, just to check, it should give me back this guy. So if I take the derivative of that, so this is my f prime, because this is f of x, big F, right? Because antiderivatives are bigs, big F's. Oh, man, my pen does not like me. All right, so if I find big F prime, just to double check that my answer gets me back to what I started with, if I take the derivative, that's negative 2, and then derivative of any is negative, so negative sine x, and the derivative of plus C is 0, so I don't need that. So negative times a negative makes a positive. It's 2 sine x. Yep, it's correct. So if you ever are unsure if you've done it right, take the derivative. You'll find out. Okay, I'm going to slide this up again so I have a little bit more room for this last trig one. Okay, so this one takes a little bit more creativity. So you need to rewrite this before you start because there is no quotient rule. There is not a quotient rule. You cannot do quotients, just derivative, or antiderivative. You can't do that. So you have to rewrite it so it's an antiderivative that you know, just like with derivatives. You can't just take the derivatives willy-nilly of each part. Same with antiderivatives. Okay, so on this one, I'm going to write this as sine x over cosine x times 1 over cosine. Essentially, I'm splitting that cosine squared into 2 pieces. Don't forget your differential. That dx at the end is important. Okay, and then I noticed right away that, well, that's special. Do you guys notice a special trig identity? I sure hope you are. This guy right here, that's tangent. Okay, so I'm going to rewrite it. Oopsie, that's my highlighter. Let's undo that one more time. All right, so that is actually the antiderivative of tangent x. Wowzer. My handwriting is getting worse and worse. I have a special stylus that helps me write. I'm not sure it's working today as well as I like it to. All right, so that's tangent. And then this other part, 1 over cosine, that part right here, 1 over cosine. Now that's secant. So we can rewrite that part as secant. So I've got tangent, secant, x, dx. Then you got to go self. Hey, that's a derivative I know. Tangent secant. What gives me a derivative of tangent secant? Psst. Tangent secant. Oh, it was secant. Secant gives me tangent secant. So it must have been secant that I started with. If this is the derivative, I can go backwards and find the original function. Don't forget your constant of integration. So if you're not sure and you can't remember, then take the derivative. This is your big F, right? It's a big F deal, right? Take the derivative of that and see if you got it right. Well, what's the derivative of secant? Well, the derivative of secant, derivative of secant is secant tangent. Hey, the derivative of any constant is plus 0, so I don't need to write that. So it got me back where I started from, just it looks a little different. So you can't use a quotient rule. Moral is you can't use a quotient rule. You have to rewrite the quotient as a derivative you do actually know. This is a derivative I know. That's the derivative of secant. So the antiderivative, secant, plus c, don't forget your constant of integration. Kind of cool. I'm going to stop the video there, and we're going to have the next video be about particular solutions. That way, it's not overwhelming to look at. This is a really good point. I would go and try to do some more of the antiderivatives CUDA sheets that I put in there for you to try, or I'm going to try to assign this Khan Academy thing, and some of you, if you're finding the CUDA sheets too easy or not easy to work through because you need a little more instruction, A, email me, or B, go to that Khan Academy site and work through some problems that they will lead you through. So I will be sharing that with you very shortly. Okay, stay tuned for the next video.